Thank you very much. Hey, I'm 4 minutes ahead of time. So thanks very much. I'm going to skip through these bits here. So these were the questions that we asked when we were trying to get to this, to looking at what we were doing. So how could we get a methodology that was cyber resilient and both technologically and economically feasible? And how do the types of security mechanism chosen contribute to the threads of evidence? How do contradictory objectives within systems and across supply ecosystems lead to security mechanisms which are costly to implement? And I don't know why I'm reading these to you, because you're all capable of reading in your own right. So I won't read the last one. Actually, the mismatches between evidence and things. And also then setting up the types of systems that we're looking at. So our observation was many of the things that we'd looked at, many of the examples that we were getting of recommendations for systems and for putting together things were based on the idea that they, or could only have been based on the idea that they were small scale systems that had a single objective. And even then it wasn't really, it was clear it wasn't really very viable to do what they were trying to do. So this was our example of how things went together, the sorts of systems we were looking at. And we sort of went through those things. We looked at the fact they got conflicting objectives in relation to those. We looked at what we were trying to do here. And this was part of our observation on resilience when we were trying to get into this, that essentially we were looking at people recommending that people harden things, which is what we generally got with the broken building over there, and the observation that very often we did perfect security systems that essentially didn't actually connect to any of the objectives that you had in relation to that, and yet the requirement was to be able to do things that actually could achieve evidence. So our view was that for cyber physical systems, the automated detection and controlling of significant difference will make it possible to obtain or make possible pattern of life evidence tying the real and the digital world. And I think that's something I'd kind of like to talk about as I go through this presentation, and talk about the things that go with that. I'll talk, if I may, about when I get down to these things. So let me do. I'm going to skip those 2 slides and do that one first. So this was the methodology and things that we came out with when we'd been going through these things. It was looking at the V models, the things that came in relation to that. And we were really looking at the first principle that we had there. So the necessity to detect, understand and act in relation to a system, and to do that with a certain probability. So our cyber resilience equation function across the bottom there was really based around the idea that if you take out what the nation is prepared to hold on to as a residual risk, and you take out what you can insure from an engineering point of view, that's what you're actually setting out to do. And as we went through this and we tried to put together the maths to actually work out what does that mean in the face of cyber attacks, what does it mean to actually be able to act on these things before you actually get to a point where things spiral out of control in really quite connected systems. We came to a conclusion that, well, firstly, that nobody's really accurately calculating this in the first place. And if you did, and you asked me to wet my finger and try and figure out what this could mean, we probably weren't talking about a better than 50% probability that I could stop a cyber attack, and a significant cyber attack, before it basically spiraled out of control and became a disaster, or as we called it, a cascade to catastrophe. And we looked at what these curves were that were actually informing that, and the curves that we had were essentially exponential curves of one sort or another on the efforts that you were putting into detection and the effort that you were putting into understanding, and possibly to a lesser extent on the stuff that you were putting into deployment. But so the observation with that one was I've essentially got to a point where on many of these where if I spend money, it doesn't make any difference to the probability that I'm going to get any of these things, and they all had that characteristic. And if you added them all together, it didn't actually add up to I was going to do much better than 50%. Maybe I could spend another $1 trillion and get up to 51%, but it was never going to give us the 99.99%, for instance, that you might want if you were looking at safety critical systems. It was never going to give you the kinds of levels of certainty that you would need if you wanted to take things to court and to prove that you had done the right engineering activity. So we introduced principle 2 here, which was looking at, well, if we could get enough difference into these things, then it would fail one at a time. And if it would fail one at a time, then we could manage the consequence in a way that we're not able to at the moment. And one of the reasons we're not able to manage the consequence is because traditional engineering techniques, and I have to say, most of the digitization methodologies that are being proposed, in fact, all of the digitization methodologies that are being proposed that I am aware of, are essentially based on some glorified version of the V model that we have in relation to this. And they concentrate on trying to make everything do the same, which essentially is great as long as it doesn't go wrong, and is an absolute disaster when it does go wrong, because it essentially means that having gone wrong, what you're actually looking at is the probability of catastrophic failure has become much greater. So we are essentially engineering for catastrophe using these methodologies, and we put some numbers around those. We looked at the probabilities. By all means, if you're looking at the chemical adherence of various types of things on a brake pad, spend a long time looking at it and try and make them all work the same way. But if you're looking at digital systems or components or systems for which a digital component is a significant part, that seems to be a really bad outcome. So when we're recommending people to engineer things in that, going forward, that was actually looking like a bad thing. So what we suggested was that we needed difference. So the first observation we got from our friends in the universities was that it wasn't just difference that we were interested in, it was significant difference. And we started looking there at some of the data science tools, and particularly some work that had been done down at Imperial at the time was looking at the use of things like Jaccard coefficients for being able to calculate whether a difference was actually part of a significant thing or not. And it appeared to us that if we were able to do that, then we would get to a much better position in relation to what we were trying to do. We put a third principle in, which was to do with how many proactive updates must you have. And this was what we based being able to calculate whether or not you had got an adequate cyber security and cyber resilience methodology or not. So when we went through looking at these sorts of things, initially the suggestion was, if you go and do this sort of stuff, the economics won't work. It only works because you make everything the same. So we essentially went through this, going from the bottom to the top, and looking at these sorts of things as we went through. Our observation was that if you look at, and I have to thank my friends at Queen's for pointing this out to me about a couple of years ago. If you looked at what was being written up as some of the most 10 most significant techniques of this decade, approximate computing was being seen as one of those things. And AI and other techniques that particularly are making use of approximate computing, where essentially we figured out that we don't necessarily need to turn everything back into a digital thing in order to be able to take advantage of it. And that's true particularly when you go down into sensors and actuators, where effectively you were looking at savings of 20% in terms of power and things if you didn't turn it back into a digital component, and you didn't need to do so in most cases. So the idea that we had behind this was, well, actually, if you look at things from the chip scale, if you look at them going up from there, if you look at the techniques that we say are going to be important to us, it looks as though things that are significantly different, or at least are different, onto which we can do calculation of difference, are actually looking at things that are the things that we're actually looking to be able to do, and which would give us the most power efficient, the most capable systems going forward. So the winners over the next decade, if you like, are not the ones that turn it back into a digital system so that you can prove that you didn't know whether it was going to fail, but actually were the ones that were increasingly able to take advantage of this. So we built the Jacquard coefficients, and I'll tell you the major problems we have in relation to that is proving the data is establishing in real time the data points against which we wish to be able to apply this technique. And then we started looking at things like automated V&V based on modeling and simulation. And that looked very promising. It also went with things like the ability to actually start to integrate into their compiler variations and things of this nature, so that our tools could start to build the sorts of things that we needed to give us a diverse system, and we could start to do the calculations in the way that we used to do so. I will tell you that there is no free lunch in relation to this. So the probability in the absolute case is going to demonstrate that you are more likely to get a failure. So yeah, on this one, so there will be outliers. You will get those kinds of things occurring, but in the aggregate case, it will be far less likely that you will be getting a catastrophic failure, which our argument is that is the one that you need to avoid. Or to put it another way, I can ensure the fact that one car crashes. I cannot ensure the fact that 40 million cars stop at the side of the road, and we've got a hiatus in our food transport system and things of this nature. Particularly if I don't know how to start 40 million cars again after. So this aspect of trying to build the difference into these sorts of things actually appeared to be something that was economically viable and indeed was economically beneficial in relation to that. And that, to the contrary, trying to do these things by doing things in the established V&V way was actually now becoming part of our problem, not part of our solution. And when we started to count this up and look at the areas that we were using this in terms of IoT devices, things that were being used into commercial, industrial, medical, the observation was that the numbers of these, this is the big market that you're looking at for the next 2 decades, but also that many of these items, and indeed the majority of these items, are now part of systems that have got safety of life implications and for which we are going to need to provide evidence. So this element of trying to bring this element of significant difference into it was one of our most significant things there. And what we did, he says, trying to get to is finished inside my 15 minutes, was then to talk about the technical approaches that we would go with that. So this is an enduring demonstrator that we've set up, looking at how we put those sorts of things together. It's based on an assumption that you need to do things like maintaining diversity and stability over the long term in your system, and to be monitoring and being able to manage that as part of doing that kind of or producing the kind of evidence that you need for regulators, for courts, and being able to take on board the mere differences that you get from for instance, different ordering of threads that you get on things. So I guess the observation, coming to some kind of a summary in relation to this, is that the work that we've been doing recently, or has been demonstrating every time we've turned a corner, that the evidence that we're getting based on V&V, based on static analysis, is fundamentally flawed. It does not take into account the complexity of the models that we're looking at in relation to those things. And therefore, our recommendation is we have to find a way to turn around and actually embrace the difference as part of trying to achieve the outcomes that we need, rather than trying to beat the difference out of a system, which will never be possible to do. So I guess that was really the points that I wanted to make in relation to this. We have not been able to find a way to do cyber resilience without introducing difference into there as a fundamental element, not just to be monitored, but also to be managed as an element of system design. And the moving of that so that we can do that as part of V&V, and so that we can do that as part of producing evidence to regulators and courts, is actually one of the things that we think is most important. So the positioning of things like distributed ledgers, so that they can record both the physical and the digital aspects, were seen as really fundamental parts of being able to do this in a cost-effective and tool-based way. And we think we were on the threshold of being able to do that. And I guess thank you for that. And if you have any questions, please ask. Otherwise, I will sort of come to a halt at that point.